guess we can start. So welcome everyone to the new semester and the second part of this lecture on the course on random matrices and universality. So yeah. I guess we've all met last year or so you all know me. So yeah, as usual, for the beginning you should register at the Moodle webpage. We'll do it similarly as last year. You will also get the homeworks on the Moodle webpage every week. I guess I'll post the first one today or maybe tomorrow. And then we'll discuss them in the exercise session the week after. And yeah, I guess that's all very organizatorial. That's all very similar to what we've done last semester. Last semester's course will not be a strict prerequisite for this course. As far as I see, you all attended it. But I will give some connections too if you need some. If we will, I mean, mostly we will use this local law, and we will extend what we have done in the very end of last lecture concerning the Kapaun correlation functions. And actually, I'll recall a few of these things today and finish the proof that was left open last semester. And yeah, if there are some questions also, you can contact me or in the break or send me an email. Okay. So maybe I quickly say what I want to do today, and then in some sense the real start of the course is next week when I give them a small introduction into what we are going to do throughout the semester. So yeah, so maybe today I recall K-point correlation function. For the eigenvalues of GUE. I'll define in a minute what all these things mean, and then there was some proof and that we still had to finish proof. I think it was proposition 45. And now I will always use a shorthand for last, if I refer to something from last semester, maybe something like this. So yeah, random matrices and universality, the first part. And then yeah, next week we'll talk about what universality really means. Yeah, I think so far we have didn't come up so off, or didn't really come up yet, introduction to the topic of this course. And yeah, that's the universality phenomenon in the random matrix theory. And yeah, the first instance will be a version of this proposition which we'll talk about today. For more general Wigner matrices. If you've forgotten what the Wigner matrix is, I'll recall also this definition next week, or you can look at the first lectures on the web from last year. Okay, so what I want to start now is of course what is written here under today, and I first want to recall and yeah, review some of the results and definitions we used last semester. And the purpose of this will not only be that you can, that if you've forgotten everything what we did last semester, you'll still understand the formulation of this proposition 45, but many of these notions will also come up again in this course, so it's maybe a good start to recall them. And I'll start with with one of the basic objects we looked at, so that's this Gaussian unitary ensemble, and let me quickly recall its definition. So I look at the matrix H, which has the following structure. We want to write it as Z plus Z star over square root 4n. It's supposed to be an n times n matrix. And this is called a Gaussian unitary ensemble. And the shortcut is GUE. In the following, I'll only use GUE because Gaussian unitary ensemble takes too much time to write. And the important thing is that the Z has a specific structure. Namely, if you can write the Z, which is also an n times n matrix, as X plus IY, where these matrices have a special structure, namely X with matrix entries Xij from 1 to n, has IID, so independent, identically distributed, normal 0, 1 entries. And Y is an independent copy of X. So in particular for Y we have the same assumption that each entry is an IID standard Gaussian. In particular Y is in distribution the same as X. Okay, so that's the basic objects. That's the basic, one basic type of matrix we looked at last semester, and then of course what we were interested in is various distributions of the eigenvalues. So I denoted them by lambda. So let lambda 1 up to lambda n be the eigenvalues of H. And yeah, in the following, you always so at least for today, we will always assume that H is a GUE matrix, and that lambda 1 up to lambda n are the eigenvalues. And I've seen that. And then maybe just to recall from last semester, the first thing we looked at was the empirical spectral measure. So we have the empirical spectral measure, which looks as follows. It's take the sum over the Dirac masses at eigenvalues, and then you normalize them, and then that converged to the semicircle distribution. So let me write it like this. So it's the measure on R, which has a density, and the density looks as follows. Okay, so you can draw a picture. So if I have the real line here, then I have somewhere the eigenvalues. And if you make n very large, so of course this is understood when n becomes very large. I don't want to be precise about the sense of the convergences. We all did last semesters. There are various types. And well, if you let n become very large, so you get many eigenvalues, then actually what you will see this semicircle distribution. Well, it should maybe be a bit more symmetric. So which is centered around 0 and goes from -2 up to 2. Okay? And today this will come up again, because now what we really want to understand today is what the correlation functions of these eigenvalues look like, and we want to study those. Okay, so that was the semicircle, and then it was the empirical spectral measure, and then we we also looked at the joint eigenvalue density. And I think the basic result we had there is, if you look at the eigenvalues and you want to understand, you look at all eigenvalues as a vector, and then you want to understand, well, for example, if they look, what's the probability that these eigenvalues lie in some kind of cylindrical event? Then we computed this last semester. This was essentially a change of variable, and one had to understand that if you can diagonalize the H with a high unitary, and then this looked as follows. You had some normalization constant and then some exponential function. And then there was this funny, so yeah, there's some exponential weight, and then you had some interaction. So yi minus yj, absolute value squared, and then you had the product Lebesgue measure dy1 up to dyn, and yeah, well, this holds for all measurable subsets of R. And if you don't believe me, or you want to go back and see what the proof was, so this was corollary 37 in the first lecture. Okay, and then the next thing we did was we looked at k-point correlation functions, and there it was somewhat helpful to look at rescaled coordinates. So consider the rescaled coordinates xi square root n yi. So in some sense that means that you blow up the semicircle if you go back and rescale them over there. And then we looked at the following measure, which is this measure just in the rescaled coordinates. So mu n x1 dxn, and that was a function rho n x1 up to xn, and then we looked at, put the rest into probability measures for the nth power of the probability measure m, probability measure mu, where so the function rho is this exponent, is this interaction. And so is this part here. So rho n from x1 up to xn, some normalization constant which I don't care about. Which will of course depend on n, and then we have the differences of the xi minus xj squared, and the mu is just the standard Gaussian measure on R. So that looks as follows. It's 1 over square root 2 pi exponential minus x squared over 2 dx. Okay, and And then we come to one of the fundamental definitions which we had here, which is the k-point correlation function with respect to this measure mu. And well, I guess you've all seen some physics, bit of physics now, maybe in the, we also recalled it last semester. So you just want to integrate out a few of these variables, and then you get the k-point correlation function. So and k-point means that, yeah, well, you integrate out all but k. So the k-point correlation function has to have k arguments. And then leave a bit of space here. There's some normalization which we'll fix in the end. So how will we do it? So we take the density rho, rho n, which has n arguments, and then we integrate all out but k of them. And of course the reference measure is still our Gaussian measure mu. Okay, so they're integrated out, but now the eigenvalues are somewhat interchangeable, so we have to have a normalization factor here, which looks as follows. It's n factorial n minus k factorial, right? Okay. And yes, and now the goal was, that was somewhat the goal of the second part of last year's or last semester's lecture. The goal was to understand this rho n k when n is large. Behavior of rho n k. And now in order to get some behavior which is to somewhat get an n-independent process, you somewhat want to look at the neighbor. You fix an energy here inside the bulk, so away from -2 and 2, and then you want to rescale the function in such a way that, well, you can expect some n-independent behavior, and for that you have to rescale it in such a way that the eigenvalues are 1 away. So we have to look on the scale of eigenvalue separation. I'll explain in a minute how we do that and how we can see it. What's the right scale here? Around, yeah, as I said, some value e well inside the support of this semicircle. Yeah, maybe I should have mentioned this here. So this is, of course, weakness semicircle. Okay, so let me draw this picture again. So we have again the real line with some eigenvalues. Well, there will be a bit denser in the middle. Well, so we have here -2, 2. We have the semicircle here, and now we fix some e somewhere inside the somewhere inside the bulk, so in the support. And now we want to understand what happens to the eigenvalues in the surrounding of this e. So we will zoom this out. Okay, so you want to rescale it in such a way that around e here, the eigenvalues somewhat have distance 1 from each other. And well, how do you have to rescale? Well, the right spacing in this scaling here looks like this, that in order to go from one eigenvalue to the next, if you have this density rho e here, then I think it's somewhat clear that if n is very large, then you have to compare the area here in a small rectangle. And what will this area be? Well, it will be the height here, rho e, times the n, because you want to have just one eigenvalue. So the distance here, well, now it's difficult. Well, maybe let me write e here. And then the distance here between two neighboring eigenvalues, distance between eigenvalues, that will be 1 over n rho e. That's what you would expect if you take, well, it's kind of a heuristic derivation, assuming that you have that you assume that the semicircle holds even on this kind of local scales. And well, by proving this proposition, which I will state next, or well, still need to introduce a little bit of notation, then I can state the proposition. And by this we will see that this is actually the right rescaling in order to get some kind of n-independent behavior. Okay, so what does this mean? That suggests that we should consider the Rescale process, namely, so the Rescaled eigenvalue process, which looks as follows. Well, I will write the process here, and instead I want to first give you what is the maybe more naive suggestion, or the more, in some sense, fundamental object is the eigenvalue process, where you just put a Dirac mass at each eigenvalue. But now we want to look at what happens here around some energy E. So we have to rescale it as follows. So we again look at Dirac masses at certain rescaled points of the eigenvalues. So we blow everything up by the eigenvalue distance here, and we center everything around the energy E. So that's now given this heuristics, that's somewhat the natural object to study if you want to get a point process which in the limit for large n gives you something non-trivial, but and of course then n independent. Okay. So that's this. That's this thing, and as I mentioned before, this concept of the k-point correlation function somewhat depends on your the measure you consider, on the reference measure, and well, the definition is still here. So in this, if I write it that way, then the reference measure is this measure mu. So in some sense, a bit more fundamental object is this intensity, k-point intensity measure. Maybe I quickly recall this, because now we will look at the different reference measure. So, well, if I say that the lambda I is a point process, this is also some recollection from last year. Maybe we had it. I think we had it on some homework. Then one can define the k-point intensity measure. That's a measure on Rk by the following way. So A is now a measurable subset of Rk. And what do I do? Well, I will do the following. I sum over all distinct combinations of points of my point process. So sum over distinct indices. And then whenever a combination of, well, you can think of the eigenvalues, for example. Whenever a k-tuple lies in this set A, then I count a 1, and I take the expectation of this measure. Okay, so what does this tell me? So let's for now think of the lambda I as being the eigenvalues, and I want to see what is the combination that k eigenvalues lie in this set AK, which is a subset of RK. And then I sum over all possible combinations of, we didn't fix any ordering of the eigenvalues, so I have to sum over all combinations of them. And then whenever I find a constellation where they lie in the set A, I get a 1, and then I take the expected contribution of this. And this is the k-point intensity measure, and this is somewhat independent of this reference measure mu I had before. So, but this contains the information which is given by the k-point correlation function because of the following. So the k-point correlation function with respect to some measure mu to some probability measure mu. Well, this was not. This is then the following measure, so you take the, you look at the density of the measure pi k with respect to the tensor product, the k-fold product measure of this reference measure mu. Okay, so and then in the case we looked at before, the mu was the Gaussian measure, and now in some sense it will turn out that the Lebesgue measure will be a more appropriate measure to understand this process here. Of course, that's not a probability measure, but there will be certain weights which make everything converge. And so just to write out the k-point intensity measure now to have an example here, in the case of GUE, I want to give you the k-point intensity measure for the eigenvalues. So this is now the standard eigenvalue process. What does the k-point intensity measure look like there? So it's the k-point correlation function, not very surprisingly. And then we have just these Gaussian weights. So because we had to multiply it with the, in that notation we have to multiply it with mu's for the x1 up to xk. So I get a e to the minus pi, no, there's no pi, e to the minus x1 squared plus xk squared over n, and then dxk. And yeah, maybe I should recall that the xi, or we use again these rescaled coordinates so that we get rid, sorry, I made too many mistakes. I hope, yeah. Of course we use the x coordinates which get rid of the n. Yeah, that was the point. They get rid of the n dependency in the exponential. So that's the, so that's the k-point intensity measure for the eigenvalue process. And yeah, well, maybe I should mention this here. So the eigenvalues means eigenvalue process. So the one where I just sum up the, where I just put Dirac mass at each eigenvalue. And now we want to look at the good object, as I tried to motivate before, is now this Rescale process. So
how lambdas and y's are connected?
Well, I mean the y is of course a variable, but they are the same, right? This is the, well, maybe it would have been better to write lambda here. So you know, the lambda are random variables. That's why I didn't want to use the same notation here. So yeah, so the lambdas correspond to the y's, and then if you rescale them by square root n, then you somehow put the eigenvalues on a bigger interval. right? In particular, an n-dependent interval. Okay. So now we can look at the same object for the rescaled process. So for the rescale process, we work with the following variables. So now we will, so yeah, as you asked, so the lambdas correspond to the y's, then we have the x variables, and now we want to, the new process, we will have alpha variables, which look as follows. So you have this rescaling by rho e times n, and then compared to the y variables, they look like this. And if I plug in the definition for the x, then I get the following. So yeah, it's just rho e n to the minus 1/2 x minus e. And maybe I should recall that what the rho of e was 1/2 pi, then the positive part of 4 minus e squared, and then a square root. Okay, so that's the semicircle density, which I drew twice now, but which both went away. And now in the beginning, we first want to fix. We first want to look at the case when e is equal to 0, because then you don't have to shift, but you just rescale, and we will see that in the computation that's a bit easier. So so we take this for simplicity, and also the rho of 0 has a nice form. You can just plug everything in. That's just 1/pi. Okay. And now we look at the k-point intensity measure again, but now of the rescale process. And yeah, now the alpha variables look as follows. Xi, okay. And so now I can just do the change of variables here in this measure. So rho n k, now it's a function. Well, I have to solve this for x. So I have a pi alpha 1 square root n up to pi alpha k square root n. Then I get the Gaussian weights. Now in the rescaled variables, maybe I write them like this. It's a bit more transparent. So pi over 2n. Alpha 1 squared up to alpha k squared. And then I get the factors from the change the measure. It's like this, and then, well, maybe I write it like this. I from 1 to k d alpha I. Okay, so that's a product measure of the Lebesgue measures. And now the good object, or now the object we want to study in the following is this coefficient here of the measure, this density. So this I want to call rho n hat k, which is a function of alpha 1 up to alpha k. And well, in some sense that's the k-point. It's now the k-point correlation function of this rescale process, but well, with respect to the Lebesgue measure, which is of course a bit, I put it in quotation marks, because in some sense this Lebesgue measure is of course not a probability measure, so this does not quite make sense, but that's kind of the way you should think about it. And then we have this remarkable result that this actually has a, when n goes to infinity, this has a nice limit, and is given by some explicit function, which will be the sine kernel, and it also reflects this determinantal point, determinantal structure which we've seen in the correlation functions. Well, somewhat on this level here last semester. So that's this proposition which we saw in the end of last semester's course. It was in some sense one of the main results. So we have k bigger than 2. We have the following, that the rho n hat k converges when n goes to infinity to some function rho k hat, where we have the locally uniformly in the k arguments here, and we have the following notations. So rho hat k of alpha 1 up to alpha k looks is defined as follows. It's the determinant of a function k hat, alpha 1, alpha I, alpha j. I take the k times k matrix, which I can combine with these arguments, and the k hat is the sine kernel. So k hat alpha beta is as follows: sine pi alpha minus beta divided by pi alpha minus beta, and that's the famous sine kernel. Well, at least in random matrix theory, and in many other instances it appears. And yeah, maybe if you remember that we saw last semester, I will recall it after the break. We saw that this rho and k have also some kind of similar structure. They're also determinants of some kernel, which is of course then n-dependent, and this limit here reflects this. And in effect, the proof will go as follows: that you start from this determinantal structure, which you can of course also see now in the rho n hat k. Just you can put all of these coefficients into the kernel. Then you get some new n-dependent kernel kn hat, and then we can see, or we will see that that was the main step that was missing last semester, which we didn't have time anymore. That this kn hat has a limit when n goes to infinity, and that's exactly this sine kernel, and that's how we'll prove this. And what does this tell you? Well, it tells you that for this GUE matrix, you can understand all k-point correlation functions of this rescale process around 0 for large n by looking at this kind of construction with the sine kernel here. And then there's also a version for the general when you shift the e. So when the e is non-zero, but between -2 and 2, then you will still have the same limit here. So that's the first instance of universality, that somehow, no matter where in the bulk you look at this rescale process, you always get the same limit. And then the first, a big part of the first lecture will be devoted to prove such a statement, but for more general ensembles, not just GUE. And yeah, maybe now's a good time for a break. And then we'll continue at 10 past. And then I'll give you the proof of this. Okay, then yeah, let's continue with the proof of this proposition. And yeah, of course, I have to recall, or I'll use certain results from the last year. So in particular, we know that the rho nk, this determinantal structure. So I first evaluated in the x coordinates, and then it looks as follows. I have the determinant of Kn. And the Kn was the following kernel. If you remember, so Kn of x and y was the sum k from 1 to n minus 1, k from 0 to n minus 1. There was some normalization constant. And then we had these orthogonal polynomials, pkx, pky, and the pk of x is the kth Hermite polynomial, which looks as follows, e to the xk dxk to the minus x squared over 2. Okay, yeah, just to have the so the pk is the case Hermite polynomial. Okay, and yeah, so that means that in particular that means that the eigenvalue process, or well, I can of course rescale by square root n. This is the determinantal point process. Maybe you've been to the mathematical physics seminar yesterday, so then you've seen another instance of a determinantal point process. They appear quite often in random matrix theory. And yeah, maybe I should give you, maybe I can squeeze it here. If you want to look at the proof of these results, these were proposition, what I used here is proposition 43, and the beginning of section 4.3 in the first part. Okay, so and then we also had a formula where we could express these kind of sums of orthogonal polynomials, and this went under the name of Christoffel Darboux. So that means that the Kn divided once more, pkx, pky. You can sum this up and write it as the following product or sum of Pn and Pn minus 1. So I have a square root n, then I have divided by square root of n factorial, square root of n minus 1 factorial, so some normalizations. And then I have Pn, so the capital N's Hermite polynomial n minus of x, and Pn minus 1 of y, and then Pn minus 1 of x and Pn of y, and divided by x minus y. Okay, so that was the due to proposition 44, the fourth part. So this was this Christoffel Darboux formula. And well, now I erased the definition of the rho n hat k, but that was a rescaled, so I had to rescale the arguments, and then I multiplied with some coefficients. So if you look at this definition carefully, then you can see that I have the same structure with another kernel for the rho n hat k at alpha 1 up to alpha k. Namely, I can write it as the determinant of rho of kn hat alpha I alpha j. And the kernel looks as follows. I will already write it in some kind of nice form. So I write it as fn of pi alpha, fn minus 1 of pi beta minus fn minus 1 pi alpha fn pi beta divided by pi alpha minus beta. And now I have to tell you what the fn's are. So fn of x is capital N to the 1/4, pi to the 1/2, 2 pi to the minus 1/4, e to the minus x squared over 4n, 1 over, now it's small n factorial, and then the square root of this, and Pn of x divided by square root n. Okay. And now, so that's the same as last year, and we had a claim which we made last year for any L in n fixed. We wanted to have the following limit statement. So we shall prove that the following convergence holds, namely the limit when n goes to infinity of fn minus L of x minus cosine of x minus n minus L p over 2. This goes to 0. Locally, uniformly in x. Okay, so I want to call this sharp. And
So in this line, all small n's and big n's are the same.
No, why? Where? In this line? When it? No, there's a small n here and a small n here. Or what is? And here there's an here there are two different arguments. So there's a capital N for the small n, or the n minus 1.
Okay. Okay.
And then yeah, here so there's the fn has a scaling coefficient here, which is n to the minus 1/4. That's a capital N, and here's a small n. I hope all of.
So small n is either n at big N minus 1 or big N.
Exactly, yes. In this line here. And then here, of course, here we will do it for general L, but actually we will only need it for L equal to 0 or L equal to 1.
So kind of this f small n of x has kind of two arguments, n small and n big, right?
Yes, yeah. So the, well, yeah. Yeah. Okay. I hope everywhere the little n and the big N are clearly distinguishable. If there's some doubt or some, then yeah, let me know. Yeah, I guess everyone has the statement. And now we will first use this sharp, so this equation which I claimed now. Just recalling the proof from the last year. We will use this to conclude the main result. So given this sharp, the claim follows for distinct. So if all of them alpha 1 up to alpha k, so if all of them are different by some standard trigonometric identity, so cosine pi alpha minus capital N times pi over 2 cosine pi beta minus n pi over 2 plus pi over 2 minus cosine pi alpha minus n pi over 2 plus pi over 2 cosine pi beta minus n pi over 2. I divide this whole thing by pi over times alpha minus beta. Then this is the sine pi alpha minus beta divided by pi times alpha minus beta. Okay, so why is this enough? Well, so now we know that the Kn hat has this structure with this kind of kernel. And, well, if you look at your notes and you look at the final result we want to prove, well, we want to prove that this converges when n goes to infinity to the determinant of k hat, where the k hat has the sign kernel, is the sign kernel. And now we know already that we would have this when there is a kn hat. And now we have these functions fn. But now by sharp, we know that these fn's all converge to some kind of cosine with some different shift and different arguments, pi times alpha or pi times beta. Then we can use this statement here to get here, in each case, the limit. Then we get these cosines. And then we can use the trigonometric identity here to get the sign. So given this sharp, and if all alphas are different from each other, then we can use this trigonometric identity, then we get the claim. There's some small argument which lifts this to the case when some alphas can be the same, or even all of them. This was presented last. This is some very short thing. I don't want to go into details there. I just refer to the last semester for the general. For general alpha 1 up to alpha k, this can be easily extended. See last lecture. So the way it went was that you could get rid of the denominator here by writing something as the integral over the derivative of these functions fn, and then you use that for these orthogonal polynomials. We have a formula for the derivative, and then essentially that means that you also have you can get an integral here, and then you get some fn minus 2 or something like this. So you can look at the last semester. So given this formula sharp, this is also trivial. And so what remains to prove is the proof of this thing. And yeah, maybe okay, so continue here. So what remains is the proof of sharp. And for this, I want to rewrite the definition, or I want to give an alternative representation of the nth Hermite polynomial. So recall that by definition, this was minus 1 to the n, e to the x squared, dxn e to the minus x squared over 2. And And I hope you have all heard of the Fourier transform, which we will use next. And if not, you can tell me after the lecture, and we can make some small homework problem out of this so that you get the basic identities which we are using. So, and what is the thing I want to use here? Well, I want to write this exponential function as a Fourier transform of something. And in fact, it's the Fourier transform of itself, namely the xn 2 pi to the minus 1/2 integral, so that's now over all of r, e to the minus x psi e to the minus psi squared over 2 d psi. Okay? So I just replace this here by its Fourier transform, and well, it's the Fourier transform of the same function, right? I hope you've seen that. If not, let me know, and then we can make a homework problem out of this. And what is the advantage of the Fourier transform? Well, the advantage of the Fourier transform is that there's a nice formula to compute the derivative, namely you can actually exchange, this of course one has to justify, you can exchange the derivative and the integral here, and then you only have to differentiate this exponential here. But this is easy to differentiate. Well, you will just, whenever you differentiate with x, you will pick up an I xi. So if you do n, you get just you get a minus I xi. So you get a minus I xi to the n. Okay. So maybe I remove the upper half of this. So now we are almost done with this rewriting. So let me just recapitulate what happened with the derivative. So yes, you pick up this minus 1, so it's e x squared over 2 pi minus 1/2 integral over r I c to the n e to the I x xi e to the c squared over 2 d xi. So yeah, maybe I should, well, yeah, somewhere here I can say maybe Fourier transform. And this here are some properties of the Fourier transform. So is everyone familiar with this formula that you can write it as this Gaussian weight as the Fourier transform of itself? And also with this formula that you can differentiate the Fourier transform, or would you prefer to have some homework problem for this? Okay, I'll think about it and maybe put some small problem there. Okay, so that was so now we have another formula for the Pn, and now I can plug in what the Fn. So now well, of course, the problem here is we have to understand these Fn's. So now I will want to rewrite this formula, the definition of Fn. So therefore, I choose now the little n to be this n minus L. And now we want to rewrite the definition of the Fn. So this is pi to the 1/2, 2 pi minus to the power minus 3/4. Then exponentially, you have to recall the Fn of x had the Pn of x over square root n. So here I get an x squared over 4n, I think. And I have a 1 over little n factorial square root n to the 1/4 integral over now this derivative formula I xi to the n e to the I xc divided by square root n. That comes from the rescaling of the x, e to the c squared dxc. Okay? And now I want to change the variables, because here this is an oscillatory factor, so when the n goes here to infinity, this will start oscillating like crazy, and this is difficult to control, so here it's better to get to move the square root n here out of the exponential, out of this out of this exponential with the imaginary unit here, so I can just rescale the xc, and then I get various powers of n. So now I change the variable, make a change of variables. So it's, well, these coefficients of course stay the same. This here is also the same. Well, let's get the square root here. So this I'll remove in a second. Then I have this n to the 1/4 here, and then by rescaling here and here, I end up with having an n to the 3/4 plus little n half, and then what I'm left with is this integral to the little n e to the I xc. And then I get an n here, n c squared over 2 dxc. Okay, so this statement we don't need anymore. Well, that's what we want to prove, but you all have it in your notes. And now to make the writing a little bit easier, I want to use the following notation, namely I want to write we write an, then this tilde, bn, to denote if the limit of their ratios converges to 1, an. And we want this convergence to hold locally uniformly in X. Okay? And then maybe the first time I use this thing is that, well, you can all convince yourself that this goes to 1. So if your X lies in some interval, so it in particular has upper and lower bounds, then when the n goes to infinity, this will converge uniformly to 1. So, and that's true for every interval, so this converges locally uniformly to 1. Okay? And now we want to approximate this factorial here by Stirling's formula to get a nicer expression for this. So, and using this notation, we want to, well, approximate this here for large n. So recall that the little n is n minus L, and I can also multiply it with this other n power, so there we will get some reasonably treatable formula. So I use the Stirling approximation for the factorial here to get the following. So this behaves like square root 2n 2 pi little n e to the n, n to the n, n to the n, capital N to the n. And, well, now I can play around with those. So first of all, I can, of course, get rid of the small l here and just replace this by an n. That will not change anything. And then I can take out this e to the n, and then what I'm left with is then n over n to the n. But this I want to rewrite, namely I want to rewrite it as follows. I smuggle in a little n, so this is n to the n plus n right? So far nothing happened, and now this is of course 1. And now you might recall that this behaves, well, this is somewhat an approximation on the exponential function. So this whole thing here together will behave like e to the, and now the argument is n to the minus n. And well, this needs a little check because somehow this n goes to infinity, and the argument here, this is just an L, right? This is an e to the L. And then I can put these two things together, so I end up with 1 over square root 2 pi n, and then there's an e to the n. This is left. So this is the behavior of this factor here. Note the square for large n. And now I will use this in the previous formula. Okay, so what do we get? Well, what we will end up with is fn of x behaves like square root pi, 2 pi to the minus 1, e to the n over 2, root n. And the integral of, and now I write it a little bit differently, xi e to the minus xi squared over 2, and the whole thing to the n. And then there's an I to the n, xi to the little n minus big N, and then there is this factor from the Fourier transform, dxi. And now if you look at the, definition, if you look at, this was roughly the definition of the Fn, but we just plugged in the xi, the Pn, the nth Hermite polynomial. But the Pn was real, actually. If you look at the definition of the Pn is real. So the Fn was just this combination times Pn. So the Fn is also real. But if I use that, then also the right-hand side here must be real. So I can just take the real part of this right-hand side here. 2 pi and now this is of course real. And then I have the real part I n e to the I c. This is also real. C little n. And this function I want to call h of xi. And if you look at it for a bit, this here will give you a shift. No, this is a phase factor actually. This is just on the unit sphere, so you can put it in the exponential here. And how will it look like? Well, it will be an I to the an e to the minus I and then n times pi over 2, right? That's how you get the I. And then you take the real part of this exponential, so that will be a cosine of x times xi minus np over 2. Okay, so yeah, of course I was wrong. This is an e to the I p n over 2, so there's no minus, and then you can just change the sign. Yeah, right. Prior there's a minus here, but the cosine is even. And now you can look at this function for a minute, and then you see that this function, wait, what did I say? The cosine is, yeah, the cosine is even. What did I do here? Ah, yes. So now you can look at this function h for a second, and you want to check what's its behavior if you reflect it around, if you look whether it's even or odd, and then it turns out it will depend on little n, because that shifts your phase. So this is minus 1 to the n h times xi. So this you can check. And here you have another, if you put these two together, you have another xi to the n. So then, therefore, the integrand is even. So recall this was an integral over r, so I can restrict everything to an integral from 0 to infinity. So let's just summarize everything. These usual coefficients, n to the 1/2, and then here I have an integral from 0 to infinity, xi e to the minus xi squared over 2 to the n. And then I have here cosine x xi n p xi to the minus n, a little n minus big N. So you see that this is minus L. And this whole guy I want to call g of xi. And the argument here I want to call f of xi. The 1/2 was cancelled by this guy. Okay, so this is the full integral. So this is twice times this integral, but I had here 1/2 there. Yeah, exactly. But and these things stay, and then 1 in the pi times the square. Okay. So now we are left with essentially, I mean, these are just coefficients. So we are left with computing this integral. And somehow this function here is more or less bounded in n. So no matter what the n does, this gives you some kind of bounded contribution. And then the important thing is what happens here with this f of xi. And you might have heard of something which is called Laplace Method. Let me explain to you what it means. So we use Laplace Method. Well, maybe analyze this integral. So from 0 to infinity, f of xi to the n, g of xi dxi, for n to infinity. So yeah, maybe this this Laplace method is a general method. Well, of course, always need some kind of assumptions. Well, maybe to determine integrals of this type. Namely, that you have an integral over some exponential n phi of xi and g of xi, and you want to analyze this for n to infinity. And essentially what this Laplace method tells you is that if the phi has a local maximum, of course the phi has to go to minus infinity when xi goes to infinity, otherwise this will not converge. But then what happens when the n goes to infinity and the phi has just one global maximum, then in fact this whole integral will be determined by some Gaussian integral or up to some n factors here determined by the maximum. But apart from that, it will be a Gaussian integral times the g evaluated at this place at the maximum. And let's see how this comes in here. Okay, so for our f, that has some, well, you can write it in a simple form. F as a unique global maximum at xi equal to 1. We have the following, namely that f of xi, we can write it as the exponential. Now the xi was positive because we restricted everything to this to the integration domain, which goes from 0 to infinity. Then I can write it as a log xi minus xi squared over 2. Well, you can now forget about the exponential and just study this here and expand it around this maximum. So and then it should look like this, right? You have a maximum, so around this everything decays. So we have a quadratic decay. And then, of course, there's some by Taylor theorem. We have some higher order term. And then what this Laplace method tells you, and we will do the details on the homework, is that actually such combination will only pick up, well, first of all, the value of Fn at the maximum. And then apart from this, you will get the Gaussian integral. And but this Gaussian integral will be centered around the maximum, which is 1 here. So, and from the g, we will only pick up the value of g at this point 1. Okay, and this basically comes from the fact that here you send the n to infinity. So this function, as you will see, well, as we will prove in the homework, will only see what happens around the maximum. And the rest will not matter. So this is somewhat completely localized around the maximum, and then you just have to evaluate the g at the maximum. So yeah, as I said, this will be done in the homework in detail. So therefore Laplace method yields that, well, maybe I should write it down once, that this, the integral we had here, so from 0 to 1, xi up to n, g of xi, dxi, this behaves like the integral of a certain Gaussian e to the minus n over 2, that comes from the value of the maximum. Then we have a e to the minus xi squared, xi minus 1 squared times n, and then a g of 1 dxi. And yeah, details on homework 1. So yeah, that's the homework I'll post today or tomorrow, and which we'll discuss next week. So today there's no homework session. Okay, so that means we can now understand this integral. So I can rewrite everything in terms of Fn, or I can plug it back. So Fn now looks like pi to the minus 1/2 e to the n over 2 n to the 1/2, and now we have this integral, minus infinity to infinity. Okay, and well, now these two guys cancel. I can pull them out, and there's a g of 1. You can plug in the definition of the g. So I end up with, well, this is an identity, pi to the minus 1/2. There's an n to the 1/2 surviving. Then I have these two things cancel. Then there's a g of 1, which is cosine of x minus n pi over 2. And then I just have this Gaussian integral. And yeah, you can convince yourself that this is pi over n. So these two things cancel. So the whole thing is cosine x minus n pi over 2. So from this we can conclude that the sharp holds, and then we have proven proposition 45. Okay. So yeah, and the details here we will do in the homework, and yeah, well, I guess you can think about it, and the point is that everything will be determined here by the maximum, because the rest is relatively small compared to the contribution of the maximum, and around the maximum you will have this contribution here. This, as I said, we'll discuss it in the homework. Okay, are there any questions about this part? And yeah, this Laplace method is really quite general, so I guess there are many instances where you can apply it, and we will just look at it in this kind of example. Okay, and now in the last few minutes, I want to look at an extension of this proposition 45, which we proved now. And in the case when the energy is somewhat general. And then, yeah, I guess I will not have time today, but then next week I'll give you some ideas of the proof. I will not present it because it will need some generalization of this Laplace method to complex exponentials. So namely when this when this exponential here is a complex argument. And that's much more technical, and I don't want to go into the details there. So now E different from 0. So what do I mean? So I want to extend proposition 45 can be extended to other E in minus 2 as well. And let me write it down in detail. So now I want to look at the case when the lambda i's, well, I guess this way in my notation the variables yi, when they were centered around an E, namely they were E plus alpha, or some non-zero E plus alpha I n rho of E. So yeah, maybe I will call semicircle. So this, now we all know it by heart. Okay, and then as before, we want to compare this with the variables xi, which were the yi times square root n. So they look as like this: square root n e plus alpha I, and now there's a square root here. Okay, and then we look at the rescaled k-point correlation function, and that will look as follows. We define the rescaled k-point correlation function around e in minus 2, 2. We define it as follows. So it has the same head, then there's an n, and there's an additional parameter e, and it will be evaluated at alpha 1 up to alpha k. So that's rho n k. So the standard, the unrescaled k-point correlation function, and then I plug in these arguments that I wrote there above. So this is alpha 1 square root n rho of e, then square root n e plus alpha k divided by square root n rho of e, and then I have the Gaussian weights, and so I have a product. So this is times the product 1 divided by 2 pi, the normalization of the Gaussian, and then there's the rho of e square root n from the rescaling, and then I have the Gaussian weight plus alpha I square root n rho of e, and this thing squared. Okay, so that's this distribution function, or the correlation function, sorry, k-point correlation function. And of course you can convince yourself that if I put in e equal to 0, then we will get back the result from before, the rescaled k-point correlation function we had before. So note that rho n0 hat of k is equal to the guy we had before in proposition 45. So that's, indicates that this is a generalization. And then I give you a statement which I will technically not prove, so I don't want to call it proposition. But, well, with a bit more effort, one could also prove it. So for any fixed e in minus 2, 2, and any fixed k in n, we have the following. We have that rho n e hat k converges to the other guy when n goes to infinity, to rho hat of k, locally uniformly. Okay, and so in some sense the e equal to 0 that we had before is not special, as long as the e lies between minus 2 and 2. And the interesting thing is that the limit will not depend on e. So no matter where you center it, the semicircle, minus 2 and 2, so as long as your e lies somewhere in between, you will always have the same as at E, well, maybe not the middle, here, you will always have the same behavior of the eigenvalues locally around this energy as you have at 0. So that's what I note, that the limit is independent of E. So that's some kind of universality, because that means that that this E is not special. But the important thing is, as long as the E lies inside, lies strictly in between -2 and 2, and yeah, there will be another limit if E is equal to plus minus 2, and that we'll treat maybe in the second half of the semester. And then yeah, next week I want to give you some ideas how to adjust the proof that we have seen before in the case when E is equal to 0 to this situation. And then we will work towards proving such kind of statement in the case when we don't have GUE, but when we have another Wigner matrix or some other Wigner matrices that we can treat in the beginning. And then actually the proof will be much different. So we will not compute the k-point correlation functions and then go through these whole things. Actually, that's not really doable in the general case, but we will rather compare it with the Gaussian case. So in some sense, we will prove that if this rho comes from a different Wigner ensemble, which is not the GUE, then it's actually close to this kind of state, these kind of observables in the case when you have a GUE, and from that you then get, by combining this with this result, you get the same kind of convergence results here. So if there's no question, then have a good day and see you next week.